Yes, so let me go over here. Let me tell you a little bit about orthogonal cutting and the turning. Before I go over there, I want to go over it again because since we are doing project, you will be doing some operation on the part which we either we provide or you bring it. It could be a small plastic uh, part rather than a metal part. We have to learn the operation rather than going to the mat. To cut the metal is a little bit harder because tools they have a lot of shearing force, cutting force, so we have to reduce the forces to. Okay, now let me show you. This process is known as the turning process. You are turning the diameter from larger diameter to the smaller diameter. This is a very big lathe machine here. So these are the deformed chip. um, After you cut the machine like metal, you have these discontinuous chips telling you this the material is not very ductile, is it chips are breaking. And when you see continuous forms of chips, the material is very ductile, malleable. So now let me tell you what is the orthogonal cutting. Okay, suppose this is a tool, and you see if the tool is coming, we will understand the orthogonal word. Ortho means 90-degree. Look, how is it 90-degree? You might be confused, professor. It doesn't look me. Look, it's like a it's like a tool. If I draw a 3D picture, look over here. The chip is coming out. Okay? Make sure you understand this. This is the tool. Suppose this is very large. Okay? Now look, this edge, this edge is perpendicular to the speed of the tool or the direction, and the cutting edge they are perpendicular. The cutting edge of this tool is this one. Try to understand. Okay, look, this is the cutting edge. This cutting edge and the tool is moving perpendicular to the cutting edge. That's why we call it orthogonal cutting. And when it is oblique, sometimes it is oblique cutting. And in orthogonal cutting, the chip is not moving to the side, but going straight up to the tool. On the rake face, we call it a rake face. Okay, in the positive rake angle. Positive rake angle, you will study it. Positive rake angle and the negative rake. Let me show you. If the tool has, suppose if the tool has configuration like this, we call it a positive rake angle. The slope is towards the back side. If the slope is towards the front side, it's a negative rake angle. Sometimes there is no angle. And you see in this is a clearance angle. I do not draw the clearance angle. And this is nothing, just the clearance angle. Okay, let me show you some of the operations here which you'll be performing here. You see basics of cutting mechanics, orthogonal, and you will be working with me, and you will be finding the MRR, material removal rate. And how do you find it out? By suppose I give you one picture. Suppose it's a turning process, okay? And the tool is moving here. Material lathe machine. It is in the lathe, okay? It is moving, and it has its own speed. And then you see the depth of cut. This is the depth of cut that the tool is inserting inside the mm, uh, cylinder, okay? This is the depth of cut, and we call this as T0. You will study what is T0, undeformed chip thickness, T1 deformed chip thickness. We will come to that later, but I want to show you how do you calculate the material removal rate. So, and you see the chip is coming out from here, and how much is this is how much is the thickness, the depth is uh, is one dimension. The second dimension is, look, if I make a tool here, tool is moving here. After some time, tool moves forward. And then in one revolution, this is W. The width of cut is equal to the motion of the tool in one revolution. Width of cut, depth of cut gives you the area, B times W. And then the speed, omega is equal to, or tangential speed equals to R omega. We call it as surface speed per minute. Surface speed per minute. Uh, we call it S. Okay, what is the units? Speed has unit meters per second. These are the two dimensions, meters and meters. Meter square, meters and meter. So meter cube per second. So material removal rate is volume removed per unit time. You understood this formula? Volume of the metal removed per unit time. It comes from this formula. And then you will see we can find out some more the energy per unit volume. Energy per unit volume. Cutting energy. So I'll come back to this later, but let's go to the next slide. Okay. And you will be doing some of the operations. If you can do more than 5 operation on the part which you will decide, then I will give you 100 out of 100 for this project. Turning, boring, milling, planing, shaping, broaching, filing. So, but this is the operation, general operation. We just have the lathe machine, or lathe machine is the computerized, but we don't have computerized lathe machine at a small scale. We have the manual lathe machine at a small scale. So you will be performing these operations. This is manual lathe. Okay. This is the boring operation. And each uh, tip has some cutting edges. If there are 4 corners, these are 4 edges. So you will see later that how to reduce the cost of manufacturing in one carbide tip or high speed steel cutting tool tip. So you see the old lathe, very old lathe. So I try to give you the background where we started this machine, how it looked like, I think this is somewhere in the museum. Do you see? So, how many? If you can perform more operation, then I will be happy. This is the project. 12 operations. Can you perform? Okay, let's see. If you perform 10 out of 12, then I'll give you 100 out of. If you perform less than 10, you will have little bit small number of points. Okay, let me take you over there to the shop upstairs.